Hello everybody, this is Alan, and today I'm going to see if I can give you guys a little bit of a tutorial on how to do an FFT on the oscilloscope. Why would we want to do an FFT? FFTs are useful on this device to help us determine what the component frequencies are making up a sinusoid that we're looking at. For example, you might look at this and say, it looks kind of like garbage. And that's because it's comprised of two simultaneous inputs at different frequencies. All right. I don't know what those frequencies are. I'm going to use the FFT to try to figure out what it is. This is just an exercise that I'm doing right now, but this is great for if you have noise in your circuit and you want to know what that frequency noise is so that you can build a filter to block it out. All right, so let's get started. First, you're going to have your signal. Make sure it's pulled up through one of your various inputs. Second, you're going to hit math. All right. Math is going to bring up this window, and if it's not selected already, you can select FFT, and then make sure that your source is set to the same channel as the input that you're using. For vertical units, typically you want to be in linear RMS window. If you take digital signal processing, then you'll learn more about this stuff. It's basically the manner in which you perform your FFT. Typically, we like to use Hanning. It's the most popular. It gives you a pretty good look at what your component frequencies are going to be made up of. Pretty decent quality. And then lastly, horizontal. You're going to want to select this, and this is going to set our window for how much frequencies at the same time. Sorry, let me reword that. This is going to help us set the window at which we look at the FFT. Okay, so what do I mean by this? So if you point your direction to this top part of the screen right here, it's a little bit obscure and hard to see, but you can actually see a window that I am moving around and shrinking and increasing. This corresponds to the entire spectrum of frequencies represented by the FFT. The FFT analyzes the entire spectrum of possible frequencies that make up this whole sine wave, no matter how small, and it represents it by this red line. It's a little bit harder to comprehend what is the limit here? It'll tell us here. Let's see. Yeah, if I go all the way to the right here, this is 50 kilohertz of frequency. We don't need all of that because I happen to know that the frequency we're looking for here, especially since I can see basically all of it when I zoom really out, is basically all to the left. All right, your amplitude, the magnitude of your frequency is represented by how far this red line goes up. So everything is over on the lower end of the frequency, so I'm going to use the bottom knob here while I'm in this menu and select it on this to zoom in my window. And then I'm going to use this to pan this window over all the way to the left. That way, I can now see my frequencies a little bit better, a little bit more spaced apart, more clear since I've zoomed in the window so far. I'm gonna decrease the size of the window just a little bit more, and now I can see this. So you can clearly see there's this peak right here, another peak there, and another peak there. I'm going to exit out of this FFT window, and I'm going to make sure that the math input is selected. I messed that up a little bit. Let me fix what I just did there. All right. So I'm going to exit out of this window, and while I am here, I now have the math input channel selected, much like how if you press the 1 button or the 2 button, you'd have the 1 or the 2 inputs selected. Now that I have the math selected, by exiting out of that window, and since I'm kind of in this menu which indicates that I am in the math input, I can turn this knob, which now increases the zoom on the magnitude of the FFT. And I'm going to zoom into 200 millivolts per division. So each one of these is the amplitude for whatever frequency it's being represented as. And then this top knob dictates the vertical offset. So if I don't like that it's all the way down here, I can bring it up to here. It's up to you. All right, so to answer our original question, what is this sine wave being made up of? I can now look and see here that it's made up of these frequencies. Now what I could do is I could look at each division and say, okay, it says that it's 500 hertz per division. So I go, okay, 0 starts at 0 right here because every FFT starts from 0 onwards. 0 hertz is here, so 500 hertz is here. This is like less than 250. If I wanted to be more exact, I can go back into FFT, go to horizontal, and then I can move the whole thing. I can slide it over to the middle. Now, I did that because this line in the middle is shown by what A is. See how A is set to 300 hertz? That's wherever it's looking at right here. So if I line this first peak up with like the center crosshair, then I can see it's made up of 150 hertz. Great. This other one seems to be made up of 75 hertz. If we look over at my AC function generator, I have 150 hertz, and I got 72 hertz. Pretty close. Well, there you have it. That, in a nutshell, is how you use the FFT to find the frequency of whatever sine wave you're looking at, and what is making the component frequencies making up that signal. I hope this was helpful, and good luck attempting this on your own. Thank you.